First, he visited US University as an exchange student. It's something to come
2001, yes.
Wow. Okay. About data, sure. Afterwards, he did his PhD in Moscow and spent a few years in Quantronics group as a postdoc. And after he moved back to Poland and established his own group, and now he leads his group, which, okay, I don't know what's the name of the group.
And it's on an official name is Kulfon.
Okay.
Which means called common, but indeed it's also. Okay,
now he tells us about some. He probably for vortices with a superconducting nanobridge. He actually spent relatively a lot of time developing nanothermometry and past nanosecond thermometry, and now it's, he will tell about application to drawing of single vortices in space. Okay.
Okay, thank you very much for the introduction, Alexander. So thank you all of you who come today to join my seminar. I'm from Institute of Physics. I brought especially for you this long stick to be able better to show. So I'm specializing in the fast time resolving nanothermometry. I will talk about this thermometry later in my talk, but kind of new range of my studies are superconducting vortices, so I try to manipulate them. So this is nanothermometry, but I will first focus on vortices, then I will introduce you to this concept of, I will show you how I measure temperature fast in nanosystems, and then I use this thermometry to also get some insight into dynamics of vortices. So let's start. So this is some teaser. We consider such box made of aluminum. Here it's 1 by 1 micrometer. This box is in immediate contact with diamond nanobridge. The diamond nanobridge is the type of Josephson junction. It has the critical current of 100 microamperes. And what is interesting about this structure, this is a very simple structure obtained with single-step emitography. Upon exceeding a certain magnetic field threshold, even small field, just a few millitesla, it traps here single vortex. And then this vortex can be, I will show you, can be detected with measuring the switching current of the bridge. So by testing the bridge with pulses, I will be able to investigate whether the vortex is here or not and to investigate different configurations. So this field, when I manipulate vortices or control their position, it's kind of new emerging field, or maybe it was already long ago, but the kind of name that I found in literature is vortex electronics. So it deals with monitoring and manipulation of vortices, both with electric current and magnetic field, to present some new functionalities, like memory cells, for example, or some logical elements, or diodes, for example. So this is roughly our hero of my today's talk. Very simple, but okay, I like simple structures because there is less room for artifacts. So you see, now we take that box, but this is the data presented for double trap or double box structure. So here this box is 1.4 micrometer wide. And when you measure its switching current characteristics as a function of perpendicular magnetic field, you see for small field the typical suppression of the switching current, which is due to Meissner effect. So Meissner screening currents circulating here in the box. They try to do whatever they can to expel the magnetic field outside, and they reduce the strength of order parameter in the vicinity of the bridge, and then the switching current is suppressed. But then at some particular value, this is very well reproducible, always happens in the same place. You find abrupt change. And this abrupt change, it corresponds to the entry of a single vortex. Actually, in this case, it's two vortices, they happen to, because the symmetric structure, so they enter to the box almost simultaneously at the same time. So this corresponds to the first vortex entry to each box. This corresponds to the two vortices in each box, three vortices in each box, and so on. So these are maps obtained in quantum simulation, time-dependent quantum simulation. I have some collaboration with guys from University of Antwerp. So how do I measure this switching current? So this is the pulse technique. I send on the junction many pulses, say 10,000, and in response to each pulse, junction may switch, but it doesn't need to switch. So it is probabilistic measurement. So if you work close here at the top of the supercurrent branch, when you sweep up the current to this plateau value, and you are close to the switching threshold, sometimes you switch, sometimes not. If you go here, obviously you never switch. If you go above, always you switch. So this is 0 probability, this is 1. But somewhere in between, you have some probabilistic behavior, and the probability, when I measure probability half, meaning that roughly half of the pulses switches, then I tell that this is my switching current. So this is the protocol. So all measurements that I do rely on the measurement of this probability. So, okay, and now if we look at various structures, various bridges, we have here single box, 2 boxes, here are just wires without boxes. You will find that here there is features, the skin, sometimes suppression, sometimes enhancement. So I will be explaining this. So these are related to the entropy, first, second, third, and so on, as I read. And then the tendency or the tendency that does the behavior is such that if you make the box bigger, then the value at which first vortex enters is lower. And okay, and this is, so you can measure for different, here we have also the switching currents corresponding to these structures, and for wires, obviously they're quite narrow, so entry happens at higher fields. Here I take one of the curves from the previous, yes, from this panel, this blue, we'll focus on this blue one now. So the blue data are experimental, and these red dots are, they come from time-dependent quantum simulation. So what we see here, that here is Meissner state. So what now I'm trying to explain what the simulation tells us, will tell us about the expected behavior. So simulation always predicts that upon exceeding certain threshold, one more vortex is added to the box, and this slightly increases the switching current. So you have whenever your vortex is present, you have jump in the switching current. So this curve corresponds to the one vortex. This one corresponds to 2 vortices. Here we have 1 vortex and 2 in second box, and so on. And then if you, so there's always an enhancement. You never predict that the switching current will be lower. And if you look at the simulation, okay, here also with these bars, you see that when you go, so these configurations are established upon field cooling of the structure. So always what I do, I first, before sending actual measuring pulse, I send the annealing pulse. So initialization pulse, which overheats my structure above TC, above 1.3 K, and now when it is inertially cooled down due to electron common coupling, the thermodynamically stable state is established, and upon exceeding certain magnetic field, this is the state with vortex. Yes, and then when you look at the simulation, well, then actually when you go up so you have such configuration, and when you want to test, you ramp up the current, and you may find these bars, they denote here the presence of one vortex, but when you exceed certain threshold, simulation actually predicts that this vortex is expelled. So when you test state without vortex. So you are on so initially with 0, the system was found in this position, but when you try to read it out during ramping up the current, vortex was expelled, so you see state without vortex. So whenever this bar doesn't go all the way to the the given curve, it means that the vortex was expelled on the way. This is the outcome of the simulation, okay? And then if you look at the order strength of the order parameter in the vicinity of the bridge, it tells you that when vortex enters, the Meissner currents, they don't need to be so strong anymore because some part of it is now taken over by the vortex. So the string doesn't need to be so strong, which means that here the smaller Meissner current in higher order parameter, so higher switching current. So intuitively, it is kind of understood that we expect that the current should be switching current should be enhanced upon each next vortex entry. Okay, and now what we want to do, we want to just mark the first vortex position entry as established from the experiment. You see that, by the way, in the experiment, it's much more sharp than the simulation. So, okay, so we take now this is the dependence for first vortex entry for box red and for Y green. And if you can fit in both, so here of the first vortex entry as a function of the inverse area of the box. So this is 1/1 micrometer squared for 1 micrometer wide box. And this has kind of intuitive physical interpretation. So according to an analytical, you may derive that the first vortex entry is, this is P/4 unity, beta is some geometrical factor, also order of unity. So whenever the flux quanta, single flux quanta is threading this area of the box, this is the condition for first vortex entry. So this is quite intuitively that we could expect that, okay, if the magnetic field creates this magnetic flux of flux quanta of the W squared, then this is energetically favorable for the system to allow one vortex entry. And here we have both experimental data, full dots, and simulation. These are these open symbols. So I must say that this is really very reproducible curve. So what we do that if we can just now design box, okay, we just from this we can do just calibration curve. So you can see that the given dots are they correspond. There are also double and single boxes here. We may give some small differences, but in principle, if you need the box with 10 milli Tesla, okay, this is the geometry that you should aim at. Okay, and now I will come back to this effect, which initially I mentioned that simulation doesn't predict expulsion of the vortex. But if we look at experimental data, these are again this first step. I could zoom in here of these transitions. So you see the change is not maybe huge. This is microamps, but it's very well measurable. So it's reproducible. So you see that, okay, this here indeed on first vortex entry, we have enhancement of the switching current. So this is, you would say, okay, I am catching by input simulation. But if you look here, it is increase, then fall down, and then increase. So, okay, this is something that we are not able to construct. And then the interpretation is that this is dissipation due to single vortex expulsion from the box. So moving vortices, they provide source of dissipation. So usually in some big structure, when you have many of them, okay, they can be responsible for quench of superconducting magnets. So the model assumes some viscous environment in which vortices are moving quasi-particles. So when you expel them with when you apply current here, you exert Lorentz force, and this force pushes it over so-called Livingston barrier. I will tell about it in a moment. But the point here, for example, how you can interpret this curve. Here you have a moment at which the first vortex enters to the box. It is stable. So when you read out your junction, you don't repel the vortex. But then at this value, second vortex enters. And this one, unlike the first, its expulsion current is lower than the switching current of the junction. So before you are able to switch, you expel it. When you expel, you create dissipation, you create quasi-particles. So you lower the order parameter. So you lower the switching current. So in fact, this is the indication of the creation of the quasi-particles in the box due to this expulsion. And then here, vortex becomes, because this is binding potential, strongly depends on magnetic field. If you increase magnetic field, vortex becomes, this global minimum becomes much and more stable. So it means that it's only the kind of region in which you can expel vortices is very close to the where they enter, and afterwards they become very stable. So you could expel them, but before you can expel them, you reach the value of the switching current. And here, similarly, this is, for example, interesting plot. Here we have first vortex entry to one of the boxes. This can be expelled with the readout current. Then second enters, so the dissipation is double. Then the first one is not, it becomes stable during readout, so you cannot expel it anymore, but second one can still expel. And then you can't expel two of them. So we come back to the kind of original paper, slightly, it should be, according to the plan, that it should be slightly. Okay. So this is just to kind of to wrap up what I have told. So this is the potential equivalent that we consider. This is Gibbs free energy as a function of the position of the vortex across the box. So middle corresponds vortex sitting here. So you see that at some fields larger than this B0, okay, vortex here is not stable situation, it goes away. At B0 starts to develop local minimum, which then becomes the global minimum. So you apply the current here, this pulse of current, which can be read out parts of your junction nanobridge, and then it works like the tilted washboard potential, which is familiar to many of you, like that with current you tilt the potential, and then the vortex may jump out. So these barriers, they are called Livingstone barriers. So they provide the capturing potential for the vortex. Okay, now I make the tour to the thermometry and then come back again to the vortices. So I developed this thermometry, which allows me to study various heat flows. So this can be hot electron diffusion, this can be electron phonon coupling, this can be emission of phonons from the nanostructure to substrate. So here the capital resistance plays a role, and then the phonon actually they travel along the substrate and they can carry the energy, they provide heat transfer channel over long distances from one nanostructure to the another on the same chip. So this is very often kind of overlooked thing, which is now kind of, I know that, okay, many people start to be interested in this because this is the source of, if you have, say, 2 qubits or single flux quantum electronics, which is only intended to be on chip to control qubit in the cold temperature, then any dissipation actually leads to this process. And this phonon travels somewhere else and hits another structure, it creates quasi-particles. So when you have qubit at 10, 20 milli K, it's really very easy to create some quasi-particles farther away. So then this mutual dissipation effects cannot be neglected. It is important to evaluate, properly understand thermal budget, yes? But okay, I will come back also to this. So let's consider such experiment in which we send here heat pulse. It creates, this is copper island. So this is done with double angle evaporation. Here is bridge 60 micrometers away. You send pulse here, and 5 nanosecond pulse. So you create quasi-particles, they start to diffuse through this neck, and after time, sometimes they should reach the bridge. So then you expect that this is the if there were no annihilation of quasi-particles on the way, you expect to see Gaussian profile with the peak at the position of the heater, which should get flattened with time. So if you look here at the bridge, at the beginning, you should not see any signal because there is some, of course, finite time for quasi-particles to arrive to the bridge. Then the signal should pick up, and then it should decay mainly due to electron phonon relaxation. So this is the experiment that you can imagine. So now we want to do it here. So we send 5 nanoseconds here, and for 10 nanoseconds, we measure the thermal response on the bridge. So what we see in experiment, yes, so this is okay, what I told. So I call it pump and probe because you heat, and then sometime later you test. So here we have data collected for 2 different polarities. So heating positive or negative to show that the effect does not depend on polarity. At time equals 0, meaning that this testing and heating pulse, they overlap. You have some crosstalk between pulses, so dependently on the polarity of heating pulse, it's up or down. But then, after this crossover this crosstalk is over, you see really no response at the detector, this distant detector. So for 30 nanoseconds, you don't see, then it picks up. At 300 nanoseconds, it reaches maximum, and then it relaxes back to the bath temperature. So this is the diffusion profile of the quasi-particle emitted from the heater. So look here at the time scale. So this is okay. Here is the linear scale. These are nanoseconds. Here is the logarithm scale. So this is actually the fastest protocol available at the moment in the world. So you can't measure better. So people usually have a resolution at the level of sub microsecond, meaning that they can measure maybe 2 points in 1 microsecond. So the protocol is a bit peculiar because it addresses only perfectly repeatable thermal processes, which can be restarted many times with the same initial conditions. But once you define your process, you can really obtain the nanosecond resolution. You can recalculate this into temperature. So now we measure these diffusion profiles at different temperatures, and they recalculated the change in probability into the change in electron temperature. Because, okay, the bridge is sensitive thermometer. It's switching probability. If when you increase temperature, you create more quasi-particles. So the switching probability is enhanced, or you may say that the switching current is low. But, okay, doing both ways, you can finally arrive to the temperature profile, temporal profile of temperature. So here you have, okay, you see these are in milli-K. So for 400 milli-K, of course, the effect is not the most pronounced. And then when you go with temperature up, then the speed becomes lower and lower. And this is because quasi-particles traveling to the junction, they are annihilated on the way due to electron phonon coupling, which becomes very effective at higher temperatures. And also they have to heat on the way other cold quasi-particles. So there is a phenomenological or heat flow equation which is taken account by the heat capacity. So this flux of diffusing quasi-particles, they have to thermalize with the local quasi-particles, and the higher the temperature, more energy goes to the phonons. That is why this diminishes, and then 800 milli-K, okay, that is measured already, is nothing left there. Also, this signal corresponds well to the expected time, diffusion time. This is the Einstein-Smallbox formula, which relates the expected arrival time of the quasi-particle with the mean squared distance between heater and the thermometer. So if you assume such diffusion constant and the distance as it is in this time, you expect that it should be 280 nanoseconds, and here it's okay, that is 300 nanoseconds. So you can consider both that this is like nice validation of the thermometer, or you can say that, okay, thermometer is, I trust my thermometer, so I consider that this is the determination of the diffusion of the diffusion constant in aluminum. Yes. Okay, and now let's go back to vortices. So let's do the same experiment, but now we put between here, here. So this is zoom in. So this is 100 micrometers. This is huge part, 400 micrometers by 400 micrometers. I depicted here schematically vortices in magnetic field. So they are not so huge, okay? So the vortex it has the diameter of coherence length, which is in this case maybe 200 nanometers. Then if I put such small dots, it's not so visible maybe. Okay, so this is the schematically depicted. Here we have thermometer. So again, what we do, we send pulse here, heating pulse, and this is probing test with switching pulse. So we send here, we create, okay, we can make different pulses of steady state, and these quasi-particles, they start to diffuse, but now we want to see if this diffusion is affected by the presence of vortices. Okay? So this is, okay, I have here collaboration with Aalto University, example for me. So we have this European microkelvin platform collaboration. So what you see, you have, again, you find with zero field, you find this familiar diffusion profile. Okay, so now what I do, I really apply, okay, 100 nanosecond pulse. This is long distance now, so I need to deliver quite a lot of power. But then when I apply field, the signal quickly diminishes. So after half minute, already it arrives almost to the saturation. I mean, it doesn't, you can increase the magnetic field further, but it doesn't want to reduce the size of the sphere. So of course, interpretation is that this is known fact that vortices act as a quasi-particle traps. So when they diffuse, they have normal force, where electron-phonon coupling is enhanced. And we expect that if we have these vortices in the path, then we should effectively block the heat transfer channel associated with quasi-particle diffusion. So this is what we expect. So in principle, I was expecting here to see that this should go to zero, but it doesn't, yes? So it stays some peak here. You can, so, okay, I will come back to this, but this is at the moment kind of puzzle. We can do the same experiment at steady state. So now it's previously it was 100 nanoseconds, now it's 100 microseconds. So we really heat long on this heater that we arrive at the steady state. So we field what we see, this 3-hour section of this map. Okay, so that's here. So we see with zero field that the switching current is suppressed. Okay, it is expected because you create quasi-particles with heater. So after time, you create some steady state population of them, and at the bridge, which is sensitive to the quasi-particle populations, and sense them. Okay, so you arrive to some steady state result. Then you can apply magnetic field, half millitesla, and you suppress it significantly. Then you can increase. These are still very small fields, but okay, you increase double, but okay, it doesn't change too much. Yes. So we have this kind of effect. On one hand, okay, we see vortices play a role, but on the other hand, we can't really kill all quasi-particles. So why doesn't it disappear completely? Let's take now do measurement is in zero field at various temperatures, 300 to 850 milliK. And what I measure here, I measure the relative suppression of the switching current. So with respect with this value, yes? So I have some value when there is no heating, and then I want to see by how many percent, this is 1%, 2%, 3%, by how many percent my switching current was suppressed due to heating pulse. So I use the same power for the heating, but I do it at different temperatures. Okay. So already I told you that electron-phonon coupling becomes very effective at high temperatures. So this is expected, yes. Okay, so I expect that perhaps that sufficiently. So yes, so this presentation allows us really to kind of blow up this. This is measured at 850 milliK. So without this kind of, if I put it as a enhancement of the change in temperature, this would be much below 1 milli Kelvin. So this effect is really very small. It requires yes, experimental effort to measure at this small temperature because it's related. So okay, and so we expect, yes, so we expect that the quasi particles are not should not reach the bridge at higher temperatures because phonons, they emit phonons on the way. Okay. So this microphone doesn't work unless a microphone is there's also a speaker, yes? Okay, I will be louder than this. Okay, so now look what I'm doing. We now have the same curves that were presented in previous plot. So red is without field. So it goes like this: 300 milli, 450, 600 milli, 800 milli. So I kept the same scale everywhere. So it's going down, down, down. But when I apply field, here is roughly 1 millitesla, and you see that, okay, the signal is smaller. This I showed you already, yes, that I can impress some, suppress some flux. But at higher field, the difference becomes smaller, and here actually it disappears at 800 milli. There is no really difference whether we applied field or not. Okay, so it looks like two components in this. So one component is field dependent, and another is not field dependent. So these are okay. These are not published data. So okay, I'm open. Somebody has some ideas. Of course, we can talk. And these are studies that I carry out within this. Okay, with Alexander and within this European microkelvin platform. So there are quite fresh data. And okay, so now we focus on this, and we do simple trick. We will subtract this peak from that one. Yes. So okay, so you have these two peaks measured in zero field, in 1 millitesla field. Then you subtract. So you consider that this one actually consists of some two components: one which you can suppress in field, another which you cannot suppress. So this is the one that you cannot suppress, and the rest of it should be something that you can suppress. So we get two peaks. And then, okay, this is like the working hypothesis that this one is actually due to phonons. So here I wrote that which travel through the so you have, say here you have emitter, here you have thermometer. So you emit, you have inside a distance, okay, you can, when you hit this part, you emit phonons, they travel ballistically, and they can carry energy over distances. And then they hit your bridge, or they can hit just the vicinity of the bridge. And then you create secondary quasi-particles, because of course, bridge cannot sense phonons, it can only sense electrons. So you need to, so you go from excess electron temperature to phonons and then back to the electrons. So this would be secondary quasi-particles which are excited in the bridge and in the adjacent lead. And there are no vortices there to manipulate quasi-particles because the lead is too narrow. So vortices can only enter into this big part, this small thing. They cannot enter to the wires, you know, from the previous studies, yes? So it would mean that phonons emitted in the silicon substrate, and then it hits somewhere in the vicinity here, and it's able to heat up the bridge independently whether you have magnetic field or not. And the second component is the one which actually you will excite some secondary quasi-particles in this big path, and then they diffuse to the path. And if there are vortices on the way, they can be manipulated. So this component, as you increase temperature, this one disappears. This one disappears. And we are left only with that one. Okay, and now I would like to make some rough calculations showing that here I put such star. So now we consider what is actually the expected arrival time for ballistic phonon from here to here. So I put parameters. So this would be the process that I described. Yeah? This is our heater thermometer. This is big parts. So these are all possible what you can do. Okay, electrons you can of course diffuse here directly. But on the way they can emit, okay, from heater you emit phonons to the substrate, and these phonons they propagate in the substrate, they bounce forward and back in silicon substrate. They create phonons in the path, and this creates secondary quasi-particles in the path. So if we consider this path, this is actually much faster than the diffusion path. Because if you take diffusion constant for quasi-particles, for 400 micrometers, the expected arrival time is 16 microseconds. But if you take this, that your phonons is just, okay, it goes just, you see, it goes here and there, with traveling with speed of sound, then you expect that after, okay, 200 nanoseconds, you should see the effect. And this is, so this calculation I put here, yes, 200 nanoseconds. So this corresponds to the onset of the signal. Yes, so, okay, so here the interesting note is that quite surprisingly, because this is our acoustic wave, you compare it with some speed of quasi-particles, that you can be faster with phonons. So on short distances, because this is Einstein's Smolkowski law, yes? So on short distances, quasi-particles are faster. But then it's because they move with some Fermi velocity, but in their diffusive motion, actually, it's much slower for them than for ballistic phonons. Okay, and now what we can do, we will cut this direct galvanic path. So I want to keep this channel. So, okay, so I kill this channel, so I have two nanostructures. So this can be, for example, SF circuit, single flux quantum circuit, and this can be QB. You do some dissipation here. Okay, they are not galvanically connected, but they sit on the same chip. And we want to see that, okay, can I transfer actually some thermal energy through this channel if it's completely galvanically isolated. So I have such structure. Here is copper heating line, and in 3 micrometers, this is here small distance. I put here the thermometer. So this is bridge, okay, bridge. And then at some further distance, I can put another one and another, so I can see actually this phonon wave as it goes, travels along the substrate. And on the way, we have, of course, this kind of processes. Okay, yeah, just systematically plotted. You can consider that you have the ballistic movement of phonons. They are created in the heater, and then this is the fastest phonon. But it can also maybe go like this. And only after several bounces arrive to the detector. Or they can make surface phonons, yes? So okay, this is some new field for me, so also I need to think how to, yes, but this is the signal that I measured. So what you see, this is the base of the signal, probability, switching probability. Higher switching probability means suppression of the order parameter in the bridge. So this is some inductive coupling because these two lines are close to each other, 3 micrometers. But then once the pulse, this 5 or 10 nanosecond pulse, excitation pulse, is over, you see immediately actually the enhancement, the probability. And then there is jump. So you get like, here you get something arrives to the bridge. So this is the time delay corresponding to delay of some particular transfer channel. And now, when you look at this time, when it starts, okay, you consider you have this limit here, distance 3 micrometers, the thickness of the silicon chip 300 micrometers, so it does take 600 divided by the speed of sound, and this is the time for which you expect this phonon to arrive. This is 100 nanoseconds, this is 100 nanoseconds. Okay, so on 2 different examples, we have that this onset of signal corresponds to the speed of sound for the transversal wave in silicon. So, okay, this is the. Now let's back. So this was big detour to this phonon. So okay, this may be now okay. This may be interesting to remember this channel. Yes, as I told, this is SFQ and as qubit. So this is it will becoming it will gain the increasing importance in analysis to keep the thermal budget of some quantum circuits under control, because these are very often overlooked things. Yes, you just want to focus on quantum effects. You don't want to think about trivial thermal effects. Yes. Okay, and now this is fancy experiment which I like. Let's replace this big part 4 by 400 micrometers with such small part 1 by 1 micrometer. So in principle, we have here excellent control. We know exactly at which field the vortex should enter here, as I showed you in the beginning of the test. So we put here heater, we put bridge, sensing bridge here, we have 30 micrometers here, 30 micrometers here. So again, the principle of this switching thermometer, we create quasi-particles here, they diffuse here, and then we switch on the field, and we want to see whether a single vortex is able to exert some influence on the flux of diffusing quasi-particles. So we want to see this single vortex by the effect it exerts, yes, on this flux. So the example, this is okay. Also, Jonas made an example for me. So example is yes, here we have bridge. Here we have this trap on the way. It is roughly 1 by 1 micrometer. And here is the sensing bridge. So this is embedded in the microwave line. And here it goes to ground. So you can, you send heating current here. And this is short path, 4 nanoseconds only. So in fact, you switch this bridge and the hotspot start to develop here. But if the path is so short that you create only bursts of quasi-particles. So you turn this part to normal state for a very short time. And the quasi-particles are created and they diffuse here, okay? So what we see, let's first do without any heating. We measure the magnetic field response, switching current response of the bridge on magnetic field. So this is this black curve. Don't know any features. This is parabola. So this is the Meissner indication of the Meissner state. So the switching current of the bridge is suppressed due to still increasing value of Meissner currents in the vicinity of the bridge, which suppress the superconducting order parameter. But now when we send this heating pulse and we measure the switching current at the time at which we expect the quasi-particles to arrive to the junction, so say this is 400, 500, 6, 7, 8, 900 nanoseconds after we send the heating pulse, then we will see that this is the zoom in of this part. So we see that upon exceeding some threshold value, the switching current is increased. So here, this value corresponds exactly to this B0 threshold value, which I defined at the beginning, which is this quantum flux quantum divided by the area of the box. So the interpretation is following that here at this field, there is no vortex, so that more quasi-particles can arrive. But as you slightly increase magnetic field, you get vortex. And when you emit these quasi-particles, some of them are annihilated on the way. So this is very small effect. You see, it's very small, but it is visible. This is just single vortex, yes? So we see the single vortex, superconducting vortex, by the effect it exerts on the flux of diffusing quasi-particles. Okay. Yes, and now I will, so how many minutes do I have? Okay, because I can show something more, yes. So this is my team. Okay, here, with these guys I'm working on daily basis. PhD student, one more PhD student, I have to put photo of her. Here is my long-standing collaborator from Aalto University, from Vascular time. Yes, so this is my scientist in Aalto. I have this collaboration with the owners on some fabrication, and this kind of information are provided by Milorad Milošević and Wyszyński University of Antwerp. So that the funding, okay, I'm funded by Foundation for Polish Science, National Science Center. So this is main source of money for me to run the science in Poland. But here I would like to acknowledge European Microkelvin platform. So many of the data that I showed examples were done within this collaboration. So I have this project here, quasi-particle diffusion and thermal relaxation in my 7 vortex states, which, okay, we have to prepare. I have to prepare nice publication on it. Okay, these are some relevant publications, but this is mainly on thermometry. I would like to show you something maybe, because I have a few minutes still, yes? So, not? No? Okay, so I should. So I will not show. So usually it is 45 minutes, yes? Okay, okay. Okay, so thank you very much. So if you have questions, so I can show you.
So I guess everything you showed.
Yes, perpendicular. No. So actually, it can withstand much higher parallel fields. So it's much more sensitive to perpendicular fields. But in parallel fields, you can't. There are no vortices, so it's not maybe so interesting. You see you see enhancement of the relaxation time. So you may say that yes. So when you have, say, relaxation electron phonon relaxation time at 300 milli-K, which is in the order of 5 microseconds, then when you apply the perpendicular field of 300 millitesla, then it will be maybe factor of 2 or 3 faster. So these are studies that you can also do. But in principle, with perpendicular field, everything is suppressed much faster. Sorry? From adding field? No, so this is in the constant field. Yes, this is constant. So what I do, my analysis is I have this kind of tricky way. I can anneal this in situ with the pulse of the current. So I either here or here I can run huge current pulse. Then I can actually turn everything this to normal state, and then I get field pulling. So because field is slow, I have big magnets, so naturally now I'm working on such small coils which would be able to have rise times of 2 microseconds, and then I could also do what would be I could apply field only after I am at low temperature. Sorry? Yes. Yeah, I must say that this is very this Oxford magnet. I have Oxford bridge. I'm very happy with this. It has very good reproducibility. Yes, so it can be that. Okay, you see this. There can be some shifts. Yes, okay, but this is, this is not shifted data, so okay, you can say that. It's usually very nicely.
So I have a question about the configuration of vortices on the blue trace that you showed.
Blue trace?
Yeah,
here.
So I would imagine when it's close to the threshold of accepting a new vortex,
yes.
that two configurations would be similarly energetically favorable.
Yes, yes.
So do you see a signature of this in the switching statistics? And why do you see such a different response for a positive field and a negative field? I imagine that this was leveraged for pulsing technique thousands of times.
Yes, yes. So this is, you see, this is vortex fields. In practice, these barriers, they are not fully symmetric because okay, they can, this is what guys usually use this magic word pinning, yes? So this can explain everything, but it means that it's easier to push vortex to one side always. And this means that because there is here, we can have, for example, some local energy minimum. And then so this one, for example, this is how, okay, Martin is in his paper about critical field for expulsion of vortices. He puts such well here and then claims that, okay, so, but this is kind of, because this is granular structure, okay, in principle, it looks that it should be perfectly, yes, I don't, but okay, but people say that because of the granularity, you don't get the ideal symmetry. Actually, this writes also some, yes, so it means that it's easier to push on this side than on that side. So it has, you may say that it behaves like vortex die.
Yeah, but this should depend on the polarity of your switching current, the current that expels it.
Yes, yes, yes.
Not on the sign of the
Yes. But okay, but this is like this asymmetry is both in field and in current.
Okay.
Yes, because then you mean, I mean then it's yes, you consider. Yeah, so I don't have the yes, it's true that this tiny details, and we have also here, you see, so obviously it works. Yes, I have also, I can show you one figure which is much stronger, this effect pronounced. Also at the beginning I showed this one. Okay, for example, here you see this bigger junction with switching current here is okay, 100, almost 200 microamps. And then this dip is really huge. So here due to expansion of a single vortex, there is huge dissipation. No, this is what I am currently studying. And the first question, what was the first?
Yeah, so do you see a signature of these configurations with similar energies in the switching statistics? So what did they adjust the mean switching current?
Yes.
But the histogram should look very different when it's close to having one or two or three vortices. This should show up as some bistable state in the switching histogram, and then based on this, you could distinguish, or at least in a structure like this, with two boxes where they go.
Okay, so I have some data in which the switching, when you try to do the switching statistics, is governed not by the stochasticity of the junction, by the stochasticity of the vortex expulsion, because there is, so once the vortex is expelled, the junction must switch, because it is in the overheated state in some sense. So then actually in the switching curves, they look completely different than okay, maybe not completely, still you have S curve, but then it's actually they can be, for example, much narrower because vortex responds in a different way. So there is, you can also study, I have such data, I didn't show them here, but you can study, for example, similar processes like this MQT or thermal escape of the particle from tilted Washburn potential. So here from this potential that I showed, also you can tilt the potential and see whether it escaped or not. And then you can try to measure similar effects for just, yes, for vortex. This stochastic. So this is something that I'm currently also doing.
How reproducible is your symmetry, say, condensed, completely all LNBM slides in both this recondensed?
Yes, so there can be small change in that these bridges are small, so there can be up to say 5%. I observe the changes in the switching current, but the characteristic is rather okay, they're very reproducible. But it can be that upon the thermal cycling, so you will not obtain exactly the same. So it can, you have to say 180, and on next cool down you get 176. So it looks like maybe it oxidized a bit, or in principle, these are very robust structures because this is okay. This is, but this may oxidize, maybe, yes. Or if you, but this is much easier to handle than the panel junctions.
Yeah, I don't think.
No, so then it's completely reproducible. Yes, if you just take it and keep it for a few months. Yeah, but I don't need to keep it at 4K. I can just apply a huge pulse of current. When I apply huge, I can overheat easily to 5K, and then I need to wait only maybe 100 microseconds or 10 microseconds. I'm back at my temperature. Yes. Yes. So this is in a kind of in situ annealing, because in fact, when I send this 10,000 pulses, each testing pulse is first I send the annealing pulse to be sure that I always restart my system in statistically the same situations. I have not done it. I have not repeated. Always it's installed in the same way.
So let's send the speaker.
Okay, thank you.